Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Cosmical giants. Exploring the vast Virgo Cluster. The Virgo Cluster is one of the most significant and well-studied galaxy clusters in the nearby universe, offering astronomers a wealth of information about the large-scale structure of the cosmos, the behavior of galaxies within clusters, and the interactions between dark matter, gas, and stars. Located approximately 53.8 million light-years from Earth in the constellation Virgo, the Virgo Cluster contains thousands of galaxies, ranging from massive ellipticals to small dwarf galaxies, and serves as the heart of the larger Virgo supercluster. The Virgo Cluster was first identified as a distinct group of galaxies in the 18th century by Charles Messier, who catalogued several of its bright member galaxies, such as M49, M58, M59, M60, M84, M86, M87, and M90. However, it wasn't until the 20th century that astronomers recognized the true scale and significance of the cluster. Today, the Virgo Cluster is known to contain over 1,300 confirmed member galaxies, with additional candidate galaxies bringing the total to over 2,000. One of the most remarkable features of the Virgo Cluster is its dynamic and diverse composition. The cluster is not a single, monolithic structure but rather a collection of several subclusters and groups of galaxies. These subclusters are in various stages of merging and interaction, making the Virgo Cluster a vibrant and complex environment. The largest and most massive subcluster is centered around the giant elliptical galaxy M87, which is one of the most massive galaxies in the universe. M87 alone contains a supermassive black hole with a mass of several billion times that of the Sun, and it is a powerful source of radio and X-ray emission. The Virgo Cluster provides a unique laboratory for studying galaxy interactions and evolution. The gravitational interactions between galaxies in the cluster lead to phenomena such as galaxy mergers, tidal stripping, and the formation of tidal tails and streams. These interactions can trigger bursts of star formation, transform spiral galaxies into elliptical galaxies, and strip galaxies of their interstellar gas, quenching their star formation. The intracluster medium, ICM, a hot, diffuse gas that fills the space between galaxies in the cluster, also plays a crucial role in galaxy evolution. The ICM emits X-rays, and its pressure can strip gas from galaxies as they move through the cluster, a process known as ram pressure stripping. One of the key discoveries about the Virgo Cluster is the presence of dark matter, an invisible substance that makes up the majority of the cluster's mass. Observations of the motion of galaxies within the cluster and the distribution of the intracluster gas have revealed that the visible matter, stars, gas, and dust, accounts for only a small fraction of the cluster's total mass. The rest is dark matter, which exerts a gravitational influence but does not emit or absorb light. The dark matter in the Virgo Cluster is thought to be distributed in a vast, diffuse halo that envelopes the entire cluster. The study of the Virgo Cluster has also provided important insights into the large-scale structure of the universe. The cluster is part of the Virgo supercluster, a vast collection of galaxy clusters and groups that spans hundreds of millions of light-years. The Virgo supercluster, in turn, is part of an even larger structure known as Laniakea, which encompasses several neighboring superclusters and forms a giant, interconnected web of galaxies. The Virgo cluster's position at the heart of these structures makes it a key reference point for mapping the distribution of galaxies in the universe and understanding the cosmic web. The Virgo cluster has been the target of numerous observational campaigns across the electromagnetic spectrum, from radio waves to X-rays. These observations have revealed a wealth of information about the cluster's galaxies, the intracluster medium, and the distribution of dark matter. The cluster's central galaxy, M87, has been studied in great detail, revealing a powerful jet of relativistic particles emanating from its supermassive black hole. This jet is visible in radio, optical, and X-ray wavelengths and extends for thousands of light-years from the galaxy's core. The Hubble Space Telescope and other advanced observatories have provided high-resolution images of the Virgo cluster's galaxies, revealing intricate details of their structure and interactions. Studies of the cluster's dwarf galaxies, which are the most numerous but faintest members, have provided insights into the formation and evolution of low-mass galaxies. These dwarf galaxies are often found in close proximity to larger galaxies, and their interactions with the intracluster medium and tidal forces from their neighbors can lead to dramatic transformations. The Virgo cluster's role as a nearby, well-studied galaxy cluster has made it a cornerstone of extragalactic astronomy. It serves as a benchmark for calibrating distance measurements to more distant galaxies, using techniques such as the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies. The cluster's proximity also makes it an ideal target for studying the detailed properties of galaxy clusters, including the distribution and dynamics of dark matter, the behavior of the intracluster medium, and the processes that drive galaxy evolution. One of the most intriguing aspects of the Virgo cluster is its ongoing assembly and evolution. The cluster is still in the process of accreting new galaxies and groups, and its structure is constantly evolving. Observations of the cluster's outskirts reveal infalling groups of galaxies that are being pulled into the cluster's gravitational well. These infalling galaxies experience intense gravitational interactions and ram pressure stripping as they enter the cluster, leading to the formation of tidal features and the disruption of their interstellar gas. The Virgo cluster's dynamic nature is also evident in the presence of substructures and anisotropies in the distribution of its galaxies and intracluster gas. Detailed studies of the cluster's X-ray emission have revealed subclusters and clumps of hot gas that trace the complex gravitational potential of the cluster. These substructures provide clues to the cluster's formation history and the processes that have shaped its current configuration. In recent years, the Virgo cluster has been a focus of studies using advanced simulation techniques. Cosmological simulations of galaxy clusters have allowed astronomers to model the formation and evolution of the Virgo cluster in a virtual universe, providing insights into the physical processes that govern the behavior of galaxies, dark matter, and the intracluster medium. These simulations have been compared with observational data to test and refine models of cluster formation and evolution, leading to a deeper understanding of the complex interplay between gravity, gas dynamics, and galaxy interactions. the study of the Virgo Cluster continues to be a vibrant and active field of research, with new discoveries and insights emerging from ongoing observations and simulations. The cluster's proximity, richness, and complexity make it an invaluable laboratory for exploring the fundamental processes that shape the universe. As new observational facilities and techniques become available, the Virgo Cluster will undoubtedly remain a cornerstone of extragalactic astronomy and a key reference point for our understanding of galaxy clusters and the large-scale structure of the cosmos.